Hi, my name is Maria. I'm gonna tell you what were my calculations for the extra credit problem of the largest jump rope. So I had to make some assumptions like the mass was 80, initial velocity was 0, and I also, from the behind the scenes, I got the length of the rope and the distance from the floor at the bottom of the jump. So the first part was to calculate the speed of the jumper at the bottom. So I used the energy principle. The initial velocity was 0, so to calculate the final velocity we already have mass, gravity, and distance from the floor, and we know that delta k plus delta u is equal to 0. So final velocity is 29.94. The second part was to calculate the tension, assuming that the cord doesn't stretch. So as you can see here, the forces acting on that person are all perpendicular to its momentum. So the parallel force is 0, so F net is equal to perpendicular force. So F tension is equal to mv squared over r plus mg. The r is the length of the rope, the mass we already know, and the velocity we take it from here. And we got that the tension force was 2,500 approximate, which is really long. Then for part 3, I had to calculate the speed and tension, but now at 30 degrees from the vertical. The process is practically the same, the distances changes. Like for example, for the first part, the distance from the ground is different, and I got it from trigonometry. We know that x, which is now the distance, the initial distance, is equal to the length of the rope times cosine 30. I use again energy principle, assuming the initial velocity is 0, and the final velocity was 25, which is smaller than the velocity at the bottom of the cord. So that makes sense because one of its fastest point is here, and here it's losing velocity now. So then for the tension force, I assume it was going in circular motion. So the tension force is equal to mv squared over r minus mg cosine 30, and I got 2000. It is smaller than before. Then the next part was to calculate the stretch at the bottom of the rope, assuming that as ideal as actual ropes do, they do stretch. So for this part, I also assumed it was a circular motion. I looked up in the internet the stiffness of a climbing rope, which is really huge, as you can see. So we expect the stretch of the rope to be small. I use energy principle, but now including the delta U of the spring. And then I use this circular to get the formula for V final, which we don't know. I plugged this into this equation, and we already have mass, distances, we have velocity, we plug this formula, and we can get the stretch of the cord. I got negative 1.3 times 10 to the negative 3. As you can see, it's really small as we predicted, and it's negative because this is my coordinate and this is 0. So S is final stretch minus initial. So final minus initial will be a negative number because of what I choose as my coordinate system. So for the next part, I had to calculate the stretch, but now at 30 degrees. So it's practically the same as this part, but now the distances change as in the third part, and I got this stretch, which is negative 2.5 times 10 to the negative 3, which is smaller number than here because of where the maximum stretch is. So now I'm going to show you what my VPython was, which was the simulation I got for the video. So as you can see, the longest stretch is at the bottom here. So this was similar to my calculations. It stretches along a lot more than it did in real life, but because it's like a simulation here, we're assuming we don't have like Air Force, and we assume a lot of things that are not in real life. But I hope this was a good explanation and you now understand this problem. So don't forget to like the video. Thanks.